Hello everyone. This video is about our project named Using Chest X-rays to Detect Pneumonia with Deep Learning. It has 3 parts: background and the data set we used, the structure of residual attention network and how did we implement it with PyTorch, and the result we get. Novel coronavirus pneumonia is a kind of pneumonia caused by COVID-19, which has become the most concerned thing in the world. The diagnosis of COVID-19 mostly depends on the nucleic acid detection, but the speed of nucleic acid detection is much slower than the speed of propagation of the virus. The diagnosis of chest X-rays is more efficient and quickly. If this detection method can guarantee a good accuracy, using this method can greatly save money and manpower. However, there is not enough dataset currently available for us. We only found hundreds of images of the COVID-19 patients on the Kaggle, which is too few to get a good result. So we want to use another dataset first to train a deep learning network, and train the model on the dataset of COVID-19 patients when it's large enough. The dataset we used is NIH Chest X-ray 14 dataset, which is released by the National Institutes of Health. It contains over 100,000 of chest X-ray images from more than 30,000 patients. Includes 14 kinds of lung diseases. Here is some example of the dataset, and red block shows where the disease is found and the label shows which kind of disease is found from the chest X-ray image. Our starting point is from this paper. ChexNet Radiologist Level Pneumonia Detection on Chest X-rays with Deep Learning. They used ChexNet, which is a 121 layer of DenseNet. And they got a very good result, which is way better than former result. And we will compare our result with this in the result part. In reality, doctors will pay more attention to important parts during diagnosis. They will focus on the area of lung on the chest X-ray image instead of other area of the image. And we found other paper from 2017 CVPR. Residual Attention Network for Image Classification. They introduced a convolutional neural network using attention mechanism, which can imitate the doctor's attention distribution when making a diagnosis. They implemented the network in Caffe, so we want to implement it in PyTorch and use it on the same task, and see whether can got a better result. We can see in the name that the residual attention network is based on the residual network. Residual net utilizes skip connections or shortcuts to jump over some layers. In this way the main part is removed and only retain the residual so it can highlight the small changes in the output. Here is our code to implement the residual block. Here is the architecture of residual attention network given in the paper. We can see that the red line has no difference with the residual network. But by add another branch named soft mask branch, we can build the attention block. Let's see the inside structure of the attention block. There are 2 branches in residual attention block: mask branch and trunk branch. Trunk branch. It is the right branch, which is for feature extraction. They can be ResNet block or other blocks. With input X, it output X. In the left is the soft mask branch. It uses bottom-up top-down structure to learn the same size mask MX. This MX is used as control gates. And the output is shown in the equation below. We can see that the attention mask can serve as feature selector during forward propagation. And it also acts as a gradient update filter during back propagation. In a word, the attention mask serves as feature selector during forward propagation, serves as gradient update filter during back propagation. That's why the model can focus on some certain area of the picture. Here is the exact architecture that we used in our project. The first one is the Residual Attention Model 56. 56 means that the trunk depth is 56. We build it by putting some attention blocks between the residual blocks. By using the block we can easily scale up to hundreds of layers. The second one is the residual attention model 92. The only difference between those two is that the number of attention block we used. There are 2 attention module stage 2 instead of 1 and 3 attention module stage 3 instead of 1 in attention 92. Here is our code to implement them, and we can see clearly that the code is almost the same, instead that we add 3 more attention block in the attention 92. Let's see inside the attention blocks. Here is the structure of the attention module stage 1. Above the dotted line is the trunk branch, which is built by 2 residual blocks. And below the line is the mask branch. We can see there are 3 downsampling and 3 upsampling, so the output size will be the same with the output from the trunk branch. Finally, we product them in element-wise and output the result to the next block. Here is our code to implement it. And here is the structure of the attention module stage 2. The difference is that there are only 2 downsampling and 2 upsampling in the mask branch. Here is our code to implement it. And here is the structure of the attention module stage 3. The difference is that there are only 1 downsampling and 1 upsampling in the mask branch. Here is our code to implement it. Here is the details for our network. The input size is the 224*220, and here are the output size, kernel size, input channel, and the stride for each layer. And after the softmax we got 14 binary classification to show whether each disease is positive or not. In training, we split their dataset 70% for training, 10% for validation, 20% for testing. With the increasing of epochs, we decreased the learning rate. In this project, we did not set the epoch with a large number, instead, we save checkpoints. If the model can be better and we still have AWS credits, we continue training with the checkpoints. It takes about 25 minutes per epoch, so the whole trains needs lots of time. Firstly, we run 10 epochs to make sure our solution works. And then we trained it for 50 epochs. We wanted to make performance better because the model is not overfitting yet. So we trained the model for 20 more epochs. However, we were short of credits at that time. Thanks to support from Professor and our mentor, we get additional $200 to continue our training, and we got our best model. The best model is 56 layers residual attention network after 90 epochs. Here is the result. We compare our result with the paper's result. AUROC is the area under the receiver operating characteristics. In the original paper they used this to evaluate their model, so we use the same way. The mean of our model is slightly lower than the paper's. Finally, there are 5 of our results better than the paper's. The result shows our group did a very great job. If a suitable dataset, enough data is made public in the future, we can train the dataset with our work and get a pretty good result based on our model. Thanks for watching.